So, welcome to the third and final plenary by Professor Martin Steinbuch, and it's called Advanced Motion Control. Our speaker is a full professor at the Eindhoven University of Technology, where he's the head of the Control Systems Technology Group of the Mechanical Engineering Department. He's also director of the Eindhoven University's Automotive Systems Graduate Program and scientific director of the Center for Competence for High-Tech Systems of the Federation of Dutch Technical Universities. He has more than 12 years of industrial experience with Philips Research Labs and Philips Center for Manufacturing Technology. He is the editor-in-chief of the IFAC Journal on Mechatronics and an associate editor of the International Journal of Powertrains. His research interests are in modeling and control of advanced motion systems, robotics for care and cure, automotive powertrains, and fusion plasmas. So let us welcome Professor Steinbuch.
Thank you, Saga, for the invitation to speak here, and also Sebastian Engel, who's not present, but he was in fact responsible for asking me. It's a pleasure to be here. It's my first time in India. I'm coming from the Netherlands, so you can imagine in the Netherlands everything on street is well organized, in complete contrast to India. So for me it was a pleasure yesterday to be in a cab during the rain flood when we were driving in the inner city. I've never seen so many people walking around just in such a pile of water on the street. And now I also understand that everybody here uses slippers and not shoes with socks normally, because with this rain you cannot really use it. But it's a great pleasure to be here. We also, like yesterday evening, the room next to ours with the dinner, where there was a wedding going on. And we were able to slip inside for just 10 minutes or so, and then we were very friendly asked to go outside again. But we got a glimpse of what a traditional marriage means here in India. It's completely different than in the Netherlands, where we have one evening of celebration and that's it, and never with 2,000 people. I mean 200 at the max or so. These are my boys, so to speak, my 3 PhD students. We got them on the camera with the 3 lovely girls sitting outside of the wedding ceremony. I also sent them this picture by email because they also like the email, I think. So it is a great pleasure to be. I will be talking about high-tech systems, and it's good for you to understand a little bit how my career went on. So I did my PhD in wind energy back in the 80s, when wind energy still was very actively done in the Netherlands. Later on, Denmark and Germany took over, and they really put a lot of money into the economic development of wind energy systems. And unfortunately in the Netherlands we didn't, so we have hardly any wind energy, although we have a lot of wind. But the control problem here was really nice. Modeling, the synchronous generator, the powertrain, electronics, and as a mechanical engineer, of course, also I did the modeling of the dynamics of the tower and the blades, and I worked on optimal control of the pitch angle in the full load conditions. And after my PhD I did in this, I went to Philips Research, and I started to work there on CD players. And after that I worked on wafer scanners, and in fact 14 years ago I moved to Eindhoven University of Technology, and I still work on wafer scanners because that has become a booming business, especially for our field of control, because they really need us, basically. And in addition, I did a lot of other applications within my group, like electron microscopes, robots for care and cure. We are doing also activities in my group on energy management and design of hybrid powertrains for trucks and passenger cars. So I will be talking about smart vehicles and also connected vehicles. And I will say a few words about plasma fusion as a new activity in my group. Now, when I started to work with Philips, they asked me, that was in the late 80s, to develop possibilities to increase the data amount and the data readout speed of CD players from nominal speed, audio, up to 4 times at that time for data, for the usage of CDs in computer applications. And the problem is that if you have a track following system, because the CD player typically has to follow the track and the focus, these are two typically controlled mechanisms. On top here there is a lens system, and there is coils around the lens and a magnet close to it, so you have a four-scroll actuator and you can control that position, and you measure the errors via the laser, and then you have a feedback loop closing that. Now if you speed up the disc, basically your set point spectrum is also amplified with a factor 4 in frequency scale, because you simply spin up the disc 4 times. You cannot measure the actual set point, because that's the absolute position of the disc in space, so to speak. So you can only measure the error. So you cannot apply feed forward, you can only do feedback. So if you would increase speed by 4, then the bandwidth should normally go a factor of 4. Now if the bandwidth typically is about, at that time, 600 Hertz, you can see what the problem is. This is the Bode plot of the open loop response of the radial tracking. So voltage into the actuator, which means current, which means force, and then you measure position relative to the track, which means the law of Newton, F equals m times acceleration. So in the Bode plot from force to position, you basically see a -2 slope, 40 decibels per decade, and at higher frequencies you see resonances. Now you can imagine if you have, the X scale is in Hertz, if you have 600 Hertz bandwidth, if you would multiply that with 4, you would have 2400 Hertz bandwidth, that's somewhere here, somewhere here, and then you are so close to flexibilities that you basically cannot do that with any robustness anymore, even if you apply sort of wide notches, then you lose too much phase. So we should be, we were asked to be more clever than PID controllers, and then I started to work on H infinity and mu synthesis and modeling uncertainties and all the things. But at a certain time I took a more deeper look into the error signals. And this is what you get with a standard PID controller, the open loop shape, in the collection at low frequencies to have additional attenuation, 600 Hertz bandwidth. This is the error signal, the spectrum, linear frequency scale of the error spectrum of this radial loop. And what you might observe is that up to 100 Hertz, you see some basic component going up, and then it's steady, but on top of that you see all those harmonics. And these harmonics are of course linked to the rotation of the disc, because at the micron scale the shape of the tracks is not a perfect circle, but it's always eccentric. That's the first harmonic, and it's always a little bit bulky at the micron scale, a little bit like a potato shape at the micron scale. So you will see a lot of higher harmonics, at least 20 harmonics. Now the PID controller did not make use of this knowledge, which basically is very stupid if you look to this spectrum, right? So what we developed then, and of course it was already known in literature before that time even, I did this in the 89 or 90, is to apply a repetitive controller, right? I should try to change the colors. You see a black line, which is a standard sensitivity, and what you might see is there is a light gray here in between. You can hardly see it. It's light gray, and these are the spikes of the repetitive controller, which is in fact an inverse COM filter. So you have a lot of inverse notches in your controller, which gives dips in your sensitivity function exactly at the places where you need it. So you suppress all harmonics, and in between you amplify, because you have to obey the Bode sensitivity integral still, because repetitive is a linear controller. Now if you apply that, and you see that in the bottom plot, you see the spectrum of a PID controlled system with a repetitive controller, and you see that all harmonics are away up to, say, 200 Hertz. So now we achieved 4 times the speed of the disc, the same error, because the cumulative error will be acceptable if you speed up the disc without any increase of bandwidth. The ball game only being look at the error spectrum and try to learn from the data of your system. Now that brought me also very close to fighting basically Bode sensitivity integral, because this is what limits our capabilities as control engineers. You have to obey this law for relative second order systems or more for any causal system. Yeah? And for linear systems it's well described using frequency domain terms, but for nonlinear systems which are causal, of course, similar things should hold. So the Bode sensitivity integral is sort of central in my work and also the lines of research I developed. It's good also for us every day to think about the basic principle of feedback. The basic principle of feedback is the principle of high gain feedback. So given a plant and a disturbance, the open loop response of course is G times D. If you close the loop, then the closed loop response from disturbance to Y is the process sensitivity. That's G times 1 over 1 plus GK, which is the sensitivity. So this is called what we call the process sensitivity. And if you have high gain, at least below the bandwidth, GK is much larger than 1 below the bandwidth. That means that this is approximately 1 over K, and the higher the gain, the smaller the output, and ultimately it will be 0. Right? This is the principle of high gain feedback, and the benefit of feedback. So the ratio of the closed loop expression over the open loop expression, this was the open loop expression, G. This is the closed loop expression. If you divide the two, you get the sensitivity function. So the sensitivity function exactly gives you what is the benefit of the feedback you designed. Right? If it's smaller than 1, you have done a great job. If it's larger than 1, you are stupid, you apply feedback. Yeah? Now if you again look to this plot, so this is the area above 1, which is not good. You amplify disturbances, we all know this. Right? We cannot stop the controller here. That would be an unstable system. So the controller will work for all frequencies, of course. And whenever we improve our performance at low frequencies, it will deteriorate at another place. So the whole ball game is to get dirt, sensitivity dirt from one place to another where it does not hurt because you don't have disturbances. That's why disturbance analysis is key. So one of the thoughts is how to cope with this Bode sensitivity, and can we in fact beat Bode? Can we crank this law? Can we circumvent this? Now some people have thought in the 80s using H infinity or LQG it will solve all problems, which is not true. If you use an observer, it's simply a filter, you have to obey Bode sensitivity. So also an LQG or an H infinity design, it uses the Bode sensitivity or has to cope with it. So it's more formal, you can play with weighting functions, but the trade-off you have to make is exactly the same, right? So, what I learned in my time in Philips, with working with real applications, is that in academia we put much too much focus on plant modeling, where we restrict the definition of plant as the system to be controlled. But we should include specifications modeling and disturbance modeling. And there's much too little literature about how to do that. And also to do more with data. It's so cheap to do experiments with motion systems. If you have a sampling frequency of 10 kilohertz, 1 second gives you 10,000 data samples. If you go to process industry and you want to have one step response, it will take you half a day. Right? So for motion systems, it's very cheap to use data. Now I want to skip now to ASML wafer scanners as an example where we all use these insights, and I will show you one of the most relevant issues we are coping currently. A wafer scanner is used in chip manufacturing, and I have a nice movie about it. I hope that the sound will work. So what you see in the movie is basically the making of a chip. Yeah? So you take a silicon structure and then you make slices of that. You call them wafers. You put them into a machine and you do a lithographic process. And you can see the lithographic process here. It's a scanning motion. And during that scanning motion, the image from the upper part of the machine, the original. Yes, that's the sound, that's good. It's not relevant for the rest, but it's something. if you keep the volume, I will play with the volume. Yeah? Okay. I need the sound later on for other videos. So this is the building of a 3D structure into chips. And you might see that these structures are becoming more and more difficult. And also the specifications are really going down, down, down. Yeah? And for every layer, this wafer has to go into the machine, lithographic process. If it's finished, it's taken out of the machine into a chemical system, a new layer spread on it, it's taken out of those ovens then, going back into the machine. That is repeated 20 to 40 times. So you take those wafers out and back in. And then you require that the chip you make has accuracies of nanometers. So all the layers should have errors of maximally nanometers compared to each other. Yeah? That's the amazing technology of wafer scanner technology. And it all began in the 70s in Philips Research, where people invented this so-called silicon repeater for very small wafers, like this, 8 centimeters, the smallest one at that time, and later on 10 centimeters, with 3 linear drives and an air mount for the other degrees of freedom. And the accuracies were microns only. And then in the early 2000s, it became 300 millimeters, like this. So you need a stage of 40 kilograms. And the specifications went down from microns to nanometers. And the machines ASML is making, ASML has 80% of the world market share of this kind of machine. This is a picture of the machine. It's huge, it's 6 meters by 2 by 4. It costs about $50 million, one machine. It's full of controls. And it's full of beautiful mechatronics and motion systems. Especially the wafer here, underneath the lens. You might see this in this video. You see here a linear drive. Yeah? The linear drive is also a 6 degree of freedom drive for the core stroke, and inside these stages there's a very small stroke of only 1 millimeter, and that's also again a 6 degree of freedom motion system, so with scrolls and magnets in all 6 degree of freedoms. Typical bandwidth is about 500 hertz for each loop, and they achieve accuracies of 2 to 3 nanometers during scanning. And the accelerations are up to 40 meters per second squared. And you can imagine that if this one is 40 kilos, such a stage, and you accelerate that with 40 meters per second squared, you get huge forces. And to achieve then a few nanometers servo errors, that's really a tough job. One of the key solutions is to have a well-defined, fine-tuned feed-forward, because you know your set points on beforehand, of course. Feed-forward is key for these machines. And then also feedback, of course, is crucial for all the disturbances which are still acting on the system. So here you see an overview of the mechanics of this system. You see the lens system, the dia, the original of the chip, which is called the reticle. It's also 6 degrees of freedom with 2 stages. And here you see the wafer stage with a balancing mass. And there are a lot of control loops here. I don't know the total amount, but it's over 80. Over 80 control loops. And each control loop cannot be seen separately because there is interaction, although they decouple the systems quite well based on physical insight and measurements. So what's the challenge? Well, the challenge is that you have to cope with at least 6 inputs by 6 outputs for each stage. You have a lot of dynamics, flexible dynamics, and up to now they could get away with PID tuning per loop and some notches to keep away of the resonances, like in the CD player. However, what is currently happening is that the whole industry wants to move from 300 millimeters to 450 millimeters. So instead of this wafer, you get this wafer, and instead of such a stage supporting the wafer, you get such a stage, which is maybe 120 kilos. And they still want to have nanometers and 40 meters per second squared accelerations. So this is an immense task. And what we foresee basically is that we have to cope with those flexibilities in a new way. We cannot simply apply notches and put them away. Yeah. So what we call this is the spatio-temporal dynamics, how to control that. And what we are investigating is to add additional actuators per stage, so not only 6 for the rigid body motions, but say 12 actuators and say 18 sensors, so that you can actually do more with feedback, that you can see more mode shapes and actively control mode shapes. Another route, and we are basically following 2 routes, is that you change the mechanics as good as possible. Now, and one of the things we research, and that's the work of Kees van Baan, one of the PhD students, he gave a talk about this morning at this conference, is that we are researching if it would be useful to add tuned mass spring damper systems. Tuned mass damper systems are often being used to prevent oscillations. The key thing is that to a structure, you add a very small mass in the order of less than 1% of that huge mass. And you tune the eigenfrequency of that small mass such that the largest deflection at that point is maximally damped by that tuned mass. However, the classical application of these tuned mass dampers is that you tune this frequency according to the frequency you want to damp. And we are doing something different, and I will show you that using this plot. This is a Bode plot of the system without the dampers. And then you add the dampers at low frequencies. So we deliberately make a very lightweight mass with a low stiffness, and the tuned mass damper has a low eigenfrequency. You see, it's not on top of one of the eigenfrequencies we would like to damp. This is the interesting area because these resonances are non-collocated, so the phase is wrong for our feedback. So these are killing us with respect to bandwidth. These we can cope with because they have a positive phase, it's collocated, right? Zeros, poles, zeros, poles. This one is killing because it's driving the phase to minus 180 additional. So we in fact want to control this one and maybe this one. Why do we put the damper here? Well, what is interesting, if we increase the damping of this tuned mass damper much more than the critical damper, you might see that first we damp its own resonance, but if we further increase the damper, and normally nobody does that, you see that the higher modes are being damped. Yeah, and it's really a strange effect. But you can imagine that physically, because basically you extract energy into the damper from the motion of that point on which you have added your mass, irrespective of the eigenfrequency. If it's moving, you extract energy. And that's, if you have a high damping value, this is the damping value on the third axis, you can see you can actually damp and you can select, the black line now is the best damper value for suppressing the amplitude of this resonance and this resonance. See? Amazing, eh? So the next step now is, this is simulation, the next step is now to make really a mechanical design for a very high damped piece and that integrated into one of the experimental systems. This is one of the experimental systems we jointly sort of can use with ASML. This is a stage structure for 450 millimeters, so this stage is about 600 millimeters. And it contains about 12 actuators and indeed about 18 sensors. And we are going to modify this structure a little bit with the tuned mass damper systems to see if we are right with our assumptions. Now, once you have done your best with the mechanical design, we have the option to do the feedback. So I will give you a few examples of the feedback principles we are working on. One of that is to make use of so-called directional notch filters. So a classical notch filter is that you have a single input, single output system and you simply have a notch filter at a certain frequency. However, if you have a multivariable system and you want to damp a certain resonance mode, this resonance mode might be seen in, say, 4 of the 6 directions. Yeah? In X, Y, and then two rotations. So if you see it in 4 directions, you might apply 4 times the same notch filter, which is then an 8th order controller. You could also modify your input-output structure, direction, so that you sort of end up with a single line, which is that mode shape. And then you put your notch there. Now that's basically what we do here. Based on model information, we make input and output transformations so as to isolate that mode, and then we put a notch in, and then we close the loop. Only for that mode. And you can then stack all the mode and all the notches together in addition to your standard single input, single output design. And you can here see that some mode is actively damped in more than one transfer function with only one notch. Now the other one is that you need very accurate models to do model-based design. Yeah? So we have in my group people working on real good system identification techniques with a control orientation. So they make very nice models, very close to the bandwidth, the intended bandwidth, with even an uncertainty estimation for the rest, so that you can use that in model-based control. One of the biggest problems here is to get reliable software for huge systems. So with many inputs and many outputs, with large time scales, it's really delicate to get numerical, reliable identification routines. As I already said, for such systems, feed-forward is key. Feed-forward is key. So one of the things we are also exploring is how to tune your feed-forwards whenever you have more actuators than actually needed for your rigid body. So suppose you have a stage, 6 degrees of freedom, standard, but you have 12 actuators. Now 6 you use for the standard feed-forward, acceleration feed-forward, but then you have 6 feed-forward channels left. What to do with that? Now one of the PhD students is working on what we call feed-forward for over-actuated systems, spatial feed-forward, and we are looking for special matrices which sort of make the direction of the mode shapes non-visible for the standard feed-forward. That's basically what you would like to do. The rigid body feed-forward should not excite your flexibilities. And you have this option if you have more inputs than rigid body motions. Now here you see some result. He also tried to do input shaping, but then you elongate a little bit your set point, and that makes your wafer throughput lower, so that's not good for the industry. And if you compare it to your original set point, you have a large error with input shaping. But with our spatial feed-forward, we can do a very nice job. You can see that here in the cumulative power spectrum of the error. So the red one is a standard rigid body acceleration feed-forward for 6 degrees of freedom applied to this system. And you see typically this resonance is very sensitive for this feed-forward. So you see an increase of your error at that frequency, and the green line completely make that effect away, and the end value is much lower than your standard rigid body feed-forward by making use of this over-actuated vector tuner. Now the last example with the ASML wafer scanner I would like to show you is making more use of data. I showed you many Bode plots already, and I also stated that it is very cheap to do experiments with motion. And those systems, ASML wafer scanners, again, have a sample frequency of 10 to 20 kilohertz. So it's easy to make a frequency response measurement. It's very difficult to make a good model. So my PhD student, he worked on, as a continuation of another PhD student, basically with the question, given a frequency response function, can we generate the frequency response for the Laplace domain? And if so, we have a non-parametric model. Can we then do pole placement with such a non-parametric model? Yeah? So only having data on the frequency, on the imaginary frequency axis, can you extend that to data in the Laplace domain? And then you can basically have all the system information you have, however in a non-parametric form. And he developed theory using complex function theory how to use that to do pole placement. And here you can see a graph where he uses a feedback controller and does pole placement. So he tunes the feedback controller gain, and he looks to the real and imaginary parts of this data, and he can tune such that he has maximum damping of the closed loop poles, which are calculated using a frequency response measurement of the plant. Yeah, which is quite strange because you don't have the need for a Laplace domain model as such. Next year he will do his PhD defense. Now, I already told you that I was sort of frustrated while working in Philips about the Bode sensitivity integral. So I put the following question. Do there exist nonlinear feedback controllers that give better performance than linear systems? For linear systems. So nobody basically is applying nonlinear control for linear systems other than sliding mode, right? But given a linear system, do there exist nonlinear controllers which do a better job than linear controllers? Well, we know if the specs are just norm-based specs, we know that the optimal solution is linear. So apparently we should think about how to change specs, more according to practice maybe. Now this is a very nice example. It goes basically back to the Lewis servo of 1953, but I like the example very much, and we replayed this design using LPV technique. What is the idea? Suppose you have a second order system, a mass controlled with a damper and a gain. And the damper normally is taken constant, and if you take it low, you have a fast response, light blue. If you take it high, you have no overshoot, dark blue, but a slow response. Right? So what we would like to have is a fast response and no overshoot. Right? What you can see is that if the error is large in the beginning, we like to have the low damping, and if the error is small, we would like to have the high damping. So why not make the differential action a function of the error? What I'm doing basically, I'm creating now a nonlinear problem because I make a nonlinear specification model. Right? Because I say, okay, my error in the beginning, I have different specs than when my error is small. The plant is still linear. So you can solve this using an LPV type of problem because basically it's LPV. So we make now the damping, our differential action, we make it now a function of the error. Yeah, and you get an LPV type of problem and you can solve that, and this is the closed loop. So you see here in black a beautiful response. Not possible with a linear feedback control. It's much better. The only trick is that you have to think about how to formulate your specifications. This is LPV on a 1953 ID. Yeah? This is another ID I really like. It's back from 1966. There were so many people so creative in it. It's called the SPAN filter, the split path nonlinear filter. So suppose the input is the error, and you rectify the error, and then you low pass the error. So all phase information is lost in the upper part. In the bottom part, you have a sign function, so you throw away all magnitude information, but you keep all phase information. And then you put that through a lead filter, giving you phase advance. And now you multiply the two signals. So the hope is that we would get a low pass with phase lead. Right? Now, is this also true? Now, we implemented this, and then we measured the Bode plot. And this is the Bode plot of this implemented filter. It is a low pass and phase lead. Right? This is the dream of every control engineer in practice, to make a low pass with phase lead with a stable filter. Now the trick, of course, is this is only the describing function. This is the first harmonic. And there will be many higher harmonics if you put in a sinusoid, because it's a nonlinear filter. So this only works if you apply it to a system with a low pass character. But most systems are. So we applied this to a motion system, to a typical fourth order system, a motor, a flexible axis, an encoder, and it works. So the black line is the line with the SPAN filter. And the dashed one is one with a classical PD-controlled system with a little bit overshoot. Same settling time. But this one, the black one, has no overshoot. Amazing, eh? The span filter. So this is sort of beating Bode in some sense. It still is causal, but you do funny things. Okay, another step in that thinking is the following. Can we use frequency response functions for nonlinear systems? And we had a very specific problem with FVI company that's also close to Eindhoven, and they make microscopes, the best microscopes in the world. They can look to picometers. The problem here is not to move fast like ASML. The problem here is to move as slow as possible. They want to move at 20 nanometers per second to scan samples. And 20 nanometers per second is the same as that you move to the chair next to you in 1.5 years. That's 20 nanometers per second. And what's the problem? The problem, of course, in their stages, that cannot be a 30 million machine. It's a 200,000 euro machine. So it's cheaper mechanics, so they have stick-slip. They have a lot of friction, they have piezo drives, stick-slip. So this is typically what you see at 20 nanometers per second. The green line would be the ideal, and this is what you get. And you can imagine that if you're an operator and you want to scan and that you see all those images coming by, that's not so nice. So what we did is the following. We put in a sinusoid and we measured the output spectrum. And then due to this friction you get a lot of higher harmonics. Now if you sum all higher harmonics, you can put it into a sort of criterion function, and we minimize that criterion function over the friction feed-forward term. So this is a means to tune the feed-forward term. It's a very simple idea, but it works really perfectly. So you can tune your feed-forward friction term by means of using higher order responses of your plant, and you try to put them to 0. If they are 0, you know that you have cancelled the nonlinearity in your plant. Hence, in this case, the friction feed-forward. Of course, your friction feed-forward model should be compatible to reality. So that always also takes time to make good friction models, of course. Now, this is about the standard motion systems, and I'm going to show you several applications of what things we do also. So for instance, medical scanners for Philips. The problem here is that often they have to do a calibration to make a 3D scan from 2D images. You need a very well calibration that you know where the patient is compared to the detector and the laser. That takes a lot of money and time. That might take a whole day to do a really good calibration. And Rick van der Maas also gave a talk here at this conference on Wednesday. He showed that using model-based techniques, you can sort of halve the time of the calibration by using model information. This is an image without calibration of a wire. It should be this image. So with a full calibration, you can get this image from your 3D processing. But with model-based supported calibration, you can already get this image with half the time. So that's where calibration comes in to really improve performance of such systems. We also worked on, and still working on, medical robotics. So this is our example to start with, intuitive surgical. You see the surgeon is sitting here with handles. Here's the robot sticking into a patient. The problem with this system, it's rather bulky, and the surgeon does not feel any force. There's no haptics involved. So we developed our own Da Vinci system. You can see it here. This is the PhD student who graduated on this. He did hold the mechanical design, and we also worked on the haptics for this. And in addition, at that same time frame, we started to do similar things for eye surgical operations, especially at the back side of the eye, at the retina. These are very tedious operations, and we have developed a master-slave system to support the surgeon, to scale his motions, and to also provide him force feedback. And this is our eye surgical robot, and you might see a small movie here. This is not an eye surgeon, by the way, but this is my PhD student. What you can see is that his right instrument is being replaced now by a master-slave system. This is the master and the slave here. And you might see in a close-up in a minute that he's having a tremor with his left hand, and the right side is completely filtered by the computer. You can see that he's having more tremor. Oh, this is also interfering. So it's irrespective of the... So a true eye surgeon would do this better, eh? They don't shake that much. The goal here is to have 10 microns accuracy at the tip, at the backside of your eye, because they want to go into veins at the retina. And that's what we can provide with this robot. So currently we are game, very good opponents. Last year in Mexico City we became world champion with in the mid-size, and this year we became second. There was a very good Chinese team who became first this year. It's really challenging, and we use this knowledge also to apply that in the care sector. So this is our care robot. That's a development of which we think that might be relevant for elderly people in due time.
I would like to participate in RoboCup 2012 on behalf of Technical Eindhoven.
So this is also one of the PhD students lying in our hospital bed, in our lab. One of the challenges here is data and object recognition, and we are participating, or we set up a project called RoboEarth, which is sort of focused on generating a sort of a Google database, but then for robots. It's called RoboEarth. So every robot on Earth could upload its learned things about the environment, and other robots can use that same knowledge. So let's make a quick step now to powertrains, because that's also a subject I really like. I think in future, cars are becoming really high-tech systems, and they will solve their own problems. So cars, they should be clean and connected, right? So I often call cars nowadays iPad on wheels. You know, a new Mercedes-Benz has 100 lines of software code. And a Boeing airplane has only 6 or so. So the software challenge in cars is huge. And also the control challenge for us people. There are so many controlled loops in a car, that's amazing. Now my great-grandfather, he was also really in automotive. He lived in early previous century. He wrote a few books on automotive, and this was his first car. I found it on internet. I think it's not electrical, although many cars were electrical at that time. And he wrote a book, and in his preface of his book he states, yeah, the problem with electrical driving is sort of that the battery is too heavy, too expensive, and the range is too low. 1930. Amazing, eh? So this will be my car. I will get it in 3 weeks from now. On September 19, they told me I can get it now in Tilburg, in Eindhoven, or in the Netherlands. It's a Tesla Model S. The US people all know this, because it's daily on the news, because the stocks are now valued $20 billion, which is as much as Renault, and as much as Peugeot and Fiat together, and half or 1/3 of General Motors or something like that, and they only make one car, which is the Tesla Model S, which is an amazing car, by the way. I've driven it a few times now. It is really amazing. It's a car with 5 adults, 2 children, 2,100 kilos, 4.2 seconds you drive 100 kilometers per hour. You don't know what happens if you press the pedal. It's amazing. And it's full of electronics. It's very easy to use. And it's quiet because it's fully electric. The whole base plate is batteries. If you buy the most expensive version, it's 85 kilowatt hours. So you can drive normally 300 miles, 450 kilometers with that. And my students last week finished the first European record. They drove 625 kilometers on one charge, on normal roads. The absolute top record is in the US. A father and a son, they drove 681 kilometers. 681 kilometers. But they drove on a test drive for 24 hours at 29 kilometers per hour on average. And my students, they drove on normal roads, but still with a modest speed, of course. The average speed was about 48 kilometers per hour. And they started in Limburg, in Vaals. That's our highest point in the Netherlands. It's only 300 meters high, but it's our highest point. Because then they could use that declination a little bit in the first part. And then they went up to Amsterdam, Haarlem, Afsluitdijk, Friesland, back to Almere. They drove here some rounds because the battery was not empty yet. And in the end they managed to have 625 kilometers on one charge. They have also made a report. It's on my blog page. If you Google Steinboeg, you will find my blog page. And the most recent blog of yesterday, in fact I made it in a hotel here, is their report about this trip. It's in English, so you can read it. They used about, on average, 130 watt-hours per kilometer, which is really low. Then, smart cars. I will make the talk. So that's about connected cars and platooning. You can see that here. If you have a normal cars and they are connected only via a radar, basically the information you get is too late, because you only measure position, right? Now what we showed with the previous PhD student, if you let them wirelessly connect, you can provide acceleration information to each other. And what you can see is that they stop immediately, right? And that's because basically in terms of motion systems, we apply now a feed forward. We apply acceleration feed forward, right? And this is so ideal. If you imagine you are in front of the traffic light and it turns green and you are fifth in a row and everybody simultaneously starts driving. That would be so nice, right? Well, sometimes in India I think that happens in fact, but without wireless communication. Yeah. So we also apply these things on the highway. That's quite unique that we have a highway where we can test these things. But I will show you another video. I hope this all works, but we will experience this. So what we did here was, in the first car, there was simply a person from TNO, an engineer. We work together with TNO. That's a Dutch research institute in the Netherlands. And the follower car, there was my PhD student of a few years ago. And that car had two options to drive. That's with a radar linked to the car in front or wireless. So we start with standard adaptive cruise control. What does it mean? You use your radar to give gas or brake. So my PhD student only needed to steer. Yeah? No touching the braking, no touch the gas pedal. What you can see basically is that the distance should be kept quite large, because if the first car brakes, it takes some time before the system realizes, hey, the position is becoming smaller, I have to brake as well. You can see that here. If the first one brakes, you see the following car makes the space smaller before he actually automatically brakes. Right? If you want to solve the mobility problem, and you have that as well here in India as in the Netherlands, we are very crowded in the Netherlands, you want to pack more cars on the highway. So here we made the distance smaller. And then you have a problem, of course, because this is a little bit tricky. If the first car immediately brakes and the second car does see that too late by only using feedback based on the position. And you will see that in a minute, that from the side there would have been an accident if not my PhD student would have done a braking. So not a braking but a turn away thing with his steering wheel. What we do now, we apply now the wireless communication. So we edit now basically acceleration feed forward from the first car using wireless communication, and that's called CACC, Cooperative Adaptive Cruise Control. And you might see now that even if we are on a small distance, the time instant that the following car is braking is almost identical to the time instant that the first car brakes. The amount of delays, it's only milliseconds because of the signal processing. You can see that beautifully here. If the first car brakes, then the second car also brakes. See? Now, I think that this is the first step towards practice of platooning. Because platooning is not necessary with 100 cars. You can do that with only 2 cars or other combinations of cars. I'm almost finished, of course, now. So let's see if this is going to work again. Yes. So my last few slides are about ITER. We work on plasma control. Why is that fun for control engineers? Basically because they need us. They are physics people. They know about the plasma, but they don't know how to control a machine. And we know. And there are huge control problems in plasma fusion. So this is a tokamak. This is a person. Yeah? So this is a huge machine being built in France by all of us. So all of the world is participating in ITER in the south of France. It should be able to work in 2026. And then it is meant to generate 10 times more power than you put in. And what we do basically is we control beams which are put inside the plasma to control turbulence and instabilities in plasma and also density profiles. That's the work we do. So typically we can measure, for instance, magnetic islands as they are called. They are local turbulence things in the plasma. You have a steerable mirror. That's how I got involved, because they had problems in their feed-forwards with the mirror, and they asked me, and then I said, okay, nice, the mirror, but how about the plasma? Because that's also adding dynamics in our feedback loop. That's about 6 years ago, and since then I'm quite successful with cooperating with the physics people. I have now about 6 PhD students in my group doing this. One of them is Rick van der Maas, and he will be given one of the, Matthijs van Berkel, he will be given one of the last talks of this conference. Eh? So please don't run away to the airport, but go to all last talks, because it will be so frustrating for them if there's nobody in the audience. So here you see a control result of a magnetic island. So at this position, that's exaggerated here, we turn on the control knob, and then you can see that we in fact can stabilize this magnetic island, and we can really close the magnetic island to 0. We also apply vision in the loop, quite nice, because we learn this from our soccer playing robots, how to use vision, real time, and we apply that now to control the edges of the plasma, because we can do edge detection using the cameras now, which is more cheap and more easy to do than with all the magnetic sensors they currently use. Now that brings me to my conclusions. I have shown you that high-tech systems are drivers for advanced control, especially in our region, ASML wafer scanners, but also the microscopes and the X-ray systems of Philips Medical. Modeling is key also of your disturbances, and do more with data. If data is cheap, use it. Don't rely only on your model. And I've shown you some examples where I think we have beat Bode, but there's still a lot of work to do. I want to thank all my collaborators, PhD students, and other people. And I want to finish with this nice video with sound.
Whoa! 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 There you go. Oh, no, you just go. Oh, my God! Oh, God! Oh. Oh, shit. Oh, nee.
Oh, what is that?
Oh, shit.
So, work should also be fun, right? Thank you.
Oh, dat is echt heel erg.
So we do have time for a couple of questions, even though we started a bit late. Are there any questions to Professor Steinbuch from the audience? Well, I guess that was a talk that was clear beyond question. So, on behalf of the organizers, I would like to give a small memento to the speaker.
Okay, thank you.